this lesson, we are going to derive the wave equation for a traveling wave that's moving down a rope or a string. If you remember when we talked about the simple harmonic oscillator, we used an equation of motion to calculate a displacement that varied with time for our oscillator. This could have been written as the position changing with time for something on a spring, or maybe even an angle changing with time for a pendulum. Now for a traveling wave, our displacements not only change with time, but they also change with space. So to understand what kind of functional forms d can take, we must first derive an equation of motion that allows us to understand this. So that's what we're going to do today. Determine a wave equation for a wave traveling down a rope or a string, but this is generally applicable to all kinds of waves. First, we have a couple of assumptions that we're going to make. So the first is that all the displacements are small. The second is that the tension everywhere inside of the rope is constant. And the third is that the wave will propagate in one dimension only. We're going to call that the x dimension. All right, so let's take a rope, a wave traveling down the rope. I'll just draw it as an object like this. And we'll say that this rope has some mass density mu. Now, to build our wave equation, we're going to start with Newton's second law. And so I'm going to take some infinitesimally small piece of rope, and I'm going to determine the forces that are felt on the rope. Okay, so on this little tiny piece, the only force that it feels is tension, and the tension on the left edge is facing this way, and the tension on the right edge is facing this way. Now we can go ahead and decompose these forces into x and y positions. So I'll go ahead and call that angle theta 1. This angle I'll call theta 2. But I know that the rope isn't actually moving to the right or to the left. All I'm going to care about are the imbalance in forces in the y direction. And that'll allow me to determine the accelerations in the y direction. So Newton's second law tells me that the sum of the forces in the y direction give me the mass times the acceleration in the y direction. And I can sum up those two forces. So facing upwards, we have a tension force, and its component is Ft sine theta 1. And facing down, we have another tension, Ft sine theta 2. I can go ahead and group these. Ft sine theta 1 minus sine theta 2. Now, to get rid of these signs, we're going to use a trig trick. So take some arbitrary triangle, all right? This is theta, this is our opposite side, this is our adjacent side, and this is our hypotenuse. And we remember that sine theta is opposite over hypotenuse, and tangent theta is opposite over adjacent. Now watch what happens when I take this triangle and make the angle really small. When that happens, the adjacent side is roughly equal to the hypotenuse. So we can go ahead and rewrite all of our sine thetas as tan thetas. And we know that tan thetas are just opposite over adjacent, which is a slope. So we can rewrite this as the slope of our rope at some position. So we can go ahead and fill that in over here. We have the slope at point 1 minus the slope at point 2. So the slope I'll just define, just to be really clear, That's the change in the displacement over space. All right, so that equals the mass times the acceleration in the y direction. Now, we can rewrite this mass for our infinitesimal window that we're looking at as just being equal to the mass density times some distance. So I'll do that. And our acceleration in the y direction is just the second derivative of our displacement with respect to time. And that equals s2 minus s. There you go. I can take all this over to this side, and I see that the acceleration is equal to ft over mu times s1 minus s2 over dx. This difference divided by some infinitesimal length is just a derivative. So that is equal to ft over mu ds dx, which can also be written as ft over mu dd dx squared. I can go ahead and rewrite this another time, just moving this term to the other side. I see that d squared d dx squared is equal to mu over ft d squared d dt squared. And if you remember, this term has shown up before in the class, and that is related to the velocity of our wave. This expression here is the 1D wave equation. And there you have it. Now, if you have a functional form for D, you can go ahead and see, does taking spatial derivatives relate to taking temporal derivatives by the velocity of the wave?